Hello viewers, my name is Dr. V. Kishen Ajay Kumar, Department of ECE, Associate Professor from the Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss the topic about the space wave propagation and the field strength of the space wave. This topic is related to the course Antennas, Waves and Propagation. The topic is regarding the space wave propagation and field strength. We are going to discuss these topics today. Let us start our session. Space wave propagation, it is a type of radio wave propagation in which the radio waves are propagated either directly from the transmitting antenna to the receiving antenna or by getting reflected from the ground. As we have seen in the earlier session in a ground wave propagation, the only difference between the ground wave propagation and space wave propagation is in terms of frequency. We can transmit a high frequency signals in the space wave propagation when compared to the ground wave propagation. You can see here the Earth. This is the surface of the Earth, and if we consider this as a transmitting antenna, and if we consider this as the receiving antenna, some electromagnetic waves are directly passing from transmitting antenna to receiving antenna, and this we call it as a direct wave, and some electromagnetic waves are getting reflected from the ground. Some are striking the surface of the Earth, and again they are reflected back to the receiving antenna. So the space wave propagation is having two paths. One is the direct path and one is the indirect path, which is known as reflection from the ground. Basically in space wave propagation, the direct transmission of signal is achieved by line of sight communication. So a direct transmission of the signal is achieved by the line of sight. So line of sight means we are going to transmit the signal directly to the receiving antenna from the transmitting antenna without any obstacles. If there are no any obstacles, if there are no any buildings or trees between the transmitting antenna and the receiving antenna, then there is a direct path between the transmitting antenna and the receiving antenna. So this form of communication, we call it as a line of sight communication. So this mode of communication, we call it as line of sight communication. So in the LOS transmission, we don't have any reflected signals as there are no any obstacles. If this is the transmitting antenna and if this is the receiving antenna, there is one direct path. So this transmission, we call it as LOS transmission or a line of sight transmission or line of sight path. So this is possible only in the space wave propagation only. The transmission of a signal between the transmitter and the receiver is achieved in the tropospheric region of the atmosphere. So not only the electromagnetic waves propagate in the ground wave, we can also transmit into free space. We can also transmit the electromagnetic waves into the tropospheric region or into the ionospheric region also. So the space wave propagation is sometimes referred to as tropospheric wave propagation. So the tropospheric waves are at a distance of 16 kilometers from the surface of the Earth. We call it that region as a tropospheric region. So if this is the surface of the Earth, from the surface of the Earth, 16 kilometers. So around 16 kilometers, we call this region as tropospheric wave propagation. The space wave propagation is possible around in this region only. So we can transmit the signal directly from the transmitting antenna to receiving antenna directly. The electromagnetic wave is propagated into the tropospheric region and it is reflected back to the receiving antenna. So this type of radio wave propagation allows the transmission of signals having a large range of frequencies. Extreme high frequencies we can transmit in the tropospheric wave region only. It means around greater than 3 megahertz. Greater than 3 megahertz to 30 megahertz. Signals, all these type of signals which comes under this range, we can transmit the signals with a large range of frequencies in this region only. That is the tropospheric wave propagation. So usually it permits the signals having a frequency greater than 30 megahertz. A frequency greater than 30 megahertz. So around we can also transmit up to 300 megahertz signals also in this region. So 30 to 300 megahertz or 300 to 3 gigahertz also we can also transmit in the space wave propagation where there is no any reflection happening in the space wave propagation. The space wave propagation is used for propagating high frequency signals by permitting direct communication between the transmitting and receiving antenna. So as we have seen now, there is a direct communication. This is the transmitting antenna and this is the receiving antenna. There is a direct communication. This is known as LOS path. So between the transmitting antenna and the receiving antenna. In case of spatial propagation, the signal without being reflected from the ionosphere simply gets propagated from an end to another in the line of sight range. Here, whenever we propagate an electromagnetic wave into the free space around a distance of 16 kilometers, it goes into the free space and it enters into the troposphere region, and there is a small refraction or reflection takes place in one of these layers in the tropospheric region, and the path is directly reached to the receiving antenna. The signal directly reaches to the receiving antenna. So this path is also known as the LOS propagation, or a line of sight propagation, or a direct transmission, or direct communication. We call this signal. That is the transmitting antenna and the receiving antenna. In space wave propagation, the electromagnetic waves are propagated when a direct path of communication is present between the sender and the receiver. Sometimes the waves are transmitted by getting reflected from the ground. Here there is a direct communication is possible, and also there is sometimes reflection from the ground is also occurs in space wave propagation. The radio waves with extremely high frequencies are known as space waves. Extremely high frequencies, that is 30 megahertz to 30 megahertz, 300 megahertz. 30 megahertz, 300 megahertz, we call it as extremely high frequencies. So we can transmit this type of high frequencies only in the space wave region only, or tropospheric region only. The troposphere allows the propagation of such waves. Generally, the troposphere is extended up to 10 to 20 kilometers above the surface of the earth. So in the region above the surface of the earth, from the region of 10 to 20 kilometers, this is the surface of the earth. From the region of 10 kilometers to 20 kilometers, and this region we call it as a tropospheric region. We call this as a tropospheric region. So in this region only the space wave propagation is possible. Thus, space wave propagation occurs at about 20 kilometers region in the atmospheric zone, sometimes called as a line of sight communication. We can also call it as a line of sight communication. This is so because high frequency waves require a direct path for propagation. So high frequency waves can be propagated, which are to be propagated, they require only the direct path for propagation. That means that free space is the only requirement we are having to propagate the signal directly to the receiving antenna, because in the free space we don't have any trees, we don't have any obstacles, we don't have any buildings. So a direct path can be established between the transmitting antenna and the receiving antenna only through the line of sight communication, that is in the tropospheric region only. As we can see in the figure shown below that, the transmitting and the receiving antennas are placed in a range where the two are present at a visible distance with respect to each other. So we can see here the transmitting and the receiving antenna, the surface of the earth is curved here. We are locating the transmitting antenna and the receiving antenna on the curved surface of the earth. So in this case, the signal emitted by the transmitting antenna gets directly received by the receiving antenna. So the transmitting antenna and the receiving antenna here both are placed in the viable distance, limited distance with respect to each other. So the transmitting antenna can be able to see the receiving antenna. At the same time, the receiving antenna is also able to see the transmitting antenna. So both are visible and are placed at the finite distance with each other. So in this case, the signal emitted by the transmitting antenna gets directly received by the receiving antenna in the absence of any obstacle. So you can see here, in this region, there are no any obstacles. In this region, there are no any obstacles or trees or any buildings between the transmitting antenna and the receiving antenna. Hence, the signal directly transmits from the transmitting antenna to the receiving antenna. So this waves we call it as a direct wave. These waves we call it as a direct wave, and some other waves touch the surface of the earth. Those are known as the reflected wave. These are known as the reflected wave, and these are known as the direct wave. So another major point of concern in the case of space wave propagation is how the range of signal transmission is specified, and how can we detect the range up to which two must be separated while installation on the surface of the earth. So another major concern in the space wave propagation is what must be the range of the signal transmission. That means at what distance the receiving antenna has to be placed from the transmitting antenna. Whether we need to place at a distance of 5 kilometers, whether we need to place the receiving antenna at a distance of 10 kilometers with respect to the transmitting antenna, we call the distance between the transmitting antenna and the receiving antenna as range of signal transmission. We call it as range. So we need to detect the range depending upon the height of. We can detect the range of communication or the range of signal transmission. It depends upon three things. One is the height of the transmitting antenna. The other one is the height of the receiving antenna, and also the distance between the distance of a propagation or the frequency. It depends upon the height of the transmitting antenna. It depends upon the height of the receiving antenna. It happens between the distance between the transmitting and the receiving antenna, and also the frequency. It depends upon the what type of signal we are going to send at the transmitting antenna, whether it is a low frequency signal or whether it is a high frequency signal. So the range of signal transmission is related to the height of the antennas concerned. The range depends upon height of the transmitting antenna and the height of the receiving antenna. To have a proper line of sight communication above the surface of the earth, the orientation of the antennas must be such that the propagated wave must not interact with the curvature of the earth. So line of sight propagation is possible only on the flat earth only. It is also possible when the earth is when the surface of the earth is curved. Under the condition that the transmitting antenna and the receiving antenna, the signal propagated to the transmitting antenna should not touch the surface. It has to reach to the receiving antenna directly without any obstacles in between the transmitting antenna and the receiving antenna. It means that when there is a surface of the earth is flat, there is no any problem. So when the surface of the earth is flat, and if this is the transmitting antenna and if this is the receiving antenna, directly we can transmit the signal. So there is no any reflection happening from the surface of the earth. Suppose if we take the curved earth, so in the flat earth it is possible for us for LOS communication. So in the flat earth it is possible for us for the LOS communication, line of sight communication. But in the case of curved earth, so whenever there is a transmitting antenna is there, so accordingly for achieving the line of sight communication, we need to place the receiving antenna in such a way that this line of sight, the receiving antenna is directly aimed towards the transmitting antenna. That means the signal that is transmitted must be directly received to the receiving antenna. In such a way, we need to increase the height of the receiving antenna according to the curvature of the earth, according to the curvature of the surface of the earth. So we can also increase the receiving antenna height so that the line of communication is possible. The line of communication is possible between the transmitting antenna and the receiving antenna. So we can adjust the height of the transmitting antenna and the receiving antenna for achieving this LOS communication. So to have LOS communication between the two antennas, the antenna units must be placed with proper orientation on the ground. So we can increase the height of the transmitting antenna, we can also increase the height of the receiving antenna. This we call it as the orientation, proper orientation on the ground. The transmitting antenna and receiving antenna heights must be adjusted. Let us calculate what is the electric field strength that has been received by the receiving antenna in space wave propagation. So let us derive an expression to find out the electric field strength at the receiving antenna in space wave propagation. So let us assume there are two types of antennas. One is the transmitting antenna, the other one is the receiving antenna. So you can see here in the figure T dash. This T dash, this is the height of the transmitting antenna, and here R dash, it represents the height of the receiving antenna. And here there are two paths. One is D1 and the D2 path. So T dash, R dash, this is known as LOS communication. This is known as LOS propagation or line of sight communication. Here this D1 represents the direct path. D1 represents the direct path from T dash to R dash. And D2 represents the indirect path, which is also known as ground reflected path. So the transmitting antenna is generating two types of signals. One is the direct signal, the other one is the indirect signal. So the direct signal goes from the T dash to the R dash, you can see in the figure, and the indirect signal goes from the path of the indirect signal is T dash O R dash. T dash O R dash, this is the reflected signal or the indirect path. So let us extend this T dash T to B. Let us extend this R dash R to A. R dash R to A. So we can also extend the T dash O like this here, like this. So let us extend the T dash O to A. So D1 is the direct path. Now T dash A, the total distance of T dash A is D2. From the figure, we can say the total distance from the T dash A, the path T dash A, we can write it as a D2. And the distance T dash R dash is equal to D1. The distance between the T dash and R dash is D1. The distance between the T dash and A is D2. And here, if we apply it, if we take this, let us redraw the figure here. This is one path, and this is another path. Let us take the surface of the earth like this, and this is the transmitting antenna, and here there is a receiving antenna, and here there is a one path here. This is D1, and this is D2. This is the height of the receiving antenna HR. This is the height of the transmitting antenna HD. Let us extend T dash O A B. T dash this is O. Let us extend this T dash O to A here, and let us extend this T dash T. This is T by dotted lines B, and join these 2 points here. T dash R dash. This is R, and extend this line and join AB here. Let us assume the distance between the T and R is the D here. The total distance between the T R is equal to B here, and the distance is the T dash R dash is equal to D1 here, and the distance between the T dash and A is D2 here. So now let us take the triangle T dash R dash R dash M here, T dash R dash M dash here. Let us assume this as join these 2 points here. This is M dash. So T dash R dash M dash. So if we take this triangle here, and this distance is D here, so M dash R dash is also D. As from the figure you can see here, M dash R dash is equal to D. So from the applying T dash R dash M dash triangle, we can write from the Pythagoras theorem. From the Pythagoras theorem, we can write here this distance as HT minus HR whole square plus D square is equal to D1 square. HT minus HR whole square plus D square is equal to D1 square. So here you can see here, this is HT total. And if we want this distance, you can see from the figure here, HT M dash R dash is D. So this we get from this triangle, we can call it as D1 square is equal to D square plus HT minus HR whole square. HT minus HR whole square. Similarly, you can take the triangle T dash AB. From the triangle T dash AB, this triangle, we can write HT plus HR whole square plus D square is equal to D2 square. So by applying the Pythagoras theorem, for the triangle T dash A and B, we can write HT plus HR. That means M dash and B. The distance between M dash B can be written as M dash, the distance between the, if we take the triangle T dash AB, we can write this T dash into B. We can write this T dash into B as HT plus HR. T dash B is equal to HT plus HR. So HT plus HR whole square is equal plus D square is equal to D2 square. So ht plus hr whole square plus d square is equal to d2 square. So from the equation 1, you can see in the figure from the equation 1, we can write d1 is equal to square root of ht minus hr whole square plus d square whole power half. So this half represents the square root. So from this equation, we can write d1 is equal to, this implies d1 is equal to d square plus ht minus hr whole square into half. So in this expression, let us take d square as common. If we take this in this expression d square as common, you will get d square into 1 plus ht minus hr by d square ht minus hr whole square by d whole square here. Whole power half you will get. So if we take this from this figure, from the equation, if we take here d square as common, you will get here d square into 1 plus ht minus hr whole square by d square. So for this total, we need to represent as square root half. So d square to the power of half is equal to, we will get only d only. So we can write overall this as a d into 1 plus ht minus hr by d whole square whole power half. Whole power half. So we can also write here 1 plus x whole from the binomial theorem. 1 plus x whole power n is equal to. So according to the expression 1 plus x whole power n is equal to, we can write 1 plus nx 1 plus nx plus n square x square plus n cubed x cubed. We are having an expression for this 1 plus x whole power n according to the binomial expansion. So based upon the binomial expansion, we can write 1 plus x here, this expression 1 plus x whole power n. Here what does x represent? ht minus hr by 2 whole square. So accordingly we can write 1 plus nx here. So 1 plus nx here, this is n. This equation we can write here as, this expression you can see here, n is equal to half here. In this equation n is equal to half here and x equal to ht minus hr by d. So half into ht minus hr by d whole square plus and so on. So as the height of the transmitting antenna and the height of the receiving antenna is larger, or if the distance is very high, and these higher order terms can be ignored. The distance is around 100 kilometers, but the height of the transmitting antenna is 100 meters only. It may be approximately 100 meters, and the height of the receiving antenna may be 80 meters approximately. So when we compare the distance with respect to the height of the transmitting antenna and height of the receiving antenna, the distance is very larger. It is around 100 kilometers or 500 kilometers. So when we divide this height of the transmitting antenna with respect to the distance, we'll get a smaller value. Hence the higher order terms can be ignored here. So accordingly, if we neglect all these higher order terms, we can write d1 is equal to d plus ht minus hr by whole square by 2d. So here from this expression, if we simplify here, ht minus hr whole square by 2d. Similarly, if we take this expression, equation 2 here, if we take this expression, that is equation 2 here, we can also write here d2 is equal to d plus ht plus hr whole square by 2d. So d2 is equal to d plus ht plus hr by 2d whole square. So we got here d1 and d2. So here from the figure you can see here, d here, d means the range, d means the distance between the transmitting antenna and the receiving antenna. So here we need to find out the path difference between the direct ray and the indirect rays. So as we have seen here, this is the transmitting antenna and this is the receiving antenna. There is a direct path here and there is a reflected path here. So T dash here, this is O, this is A, this is B, and this is M dash, this is R dash, RT, this is R. Let's assume this as a T here. Join these two here. Let's assume this as M dash. Here, whenever the signal is being propagated from the transmitting antenna here, there are two types of race paths we are getting from the transmitting antenna. One is the direct path and the other one is indirect path. Here, the distance between the direct path, that is D1, the signal D1 along the path D1 will reach to the receiving point R dash earlier when compared to the indirect path. So the signal from T dash to R, which is the line of sight communication, the path from the T dash to R dash, that signal will reach to the receiving antenna earlier when compared to the indirect signal, that is the T dash O R dash. So T dash R dash will reach earlier when compared to the path T dash O R dash, which is the indirect path. So as these two waves are going to reach to the receiving point at a different time intervals, there is a path difference. There is a path difference between the direct ray and the indirect path. So when there is a difference between the path difference, then definitely there will be some phase difference. Definitely there will be some phase difference between the two electromagnetic signals propagated by the transmitting antenna. Let us find out the path difference first. So D2 minus D1. So we got in the previous slide, that is D1 and D2, equation 3 and equation 4. Let us do this differentiation to find out the path difference D2 minus D1 here. So equation 4 minus 3, substitute, if you simplify, you will get the path difference as 4HD HR by 2D. 4HD HR by 2D. You can also simplify this as HT HR by D. You can also simplify this as HT HR by D. So as there is a path difference, there is a phase difference. So the phase difference due to the path difference is given by alpha is equal to 2 pi by lambda into path difference. Alpha is the phase difference, alpha is the parameter. It is a symbol represented for the phase difference. It is the symbol represented for the phase difference, which is given by the 2 pi by lambda into path difference. So as we have seen, the path difference is 4HT HR by 2D. So in the previous slide, we have seen alpha is equal to 2 pi by lambda 4HT HR by 2D. So if we simplify this expression, we will get alpha is equal to 4 pi HT HR by D lambda. Alpha is equal to 4 pi HT HR by D lambda. So this is the phase difference caused due to the path difference. This is the phase difference caused due to the path difference. So we have found out phase difference due to the path difference. Due to the path difference. So here there is another phase difference of 180 degrees due to the reflections from the ground. So as we have seen here, this is the surface of the earth, and this is the transmitting antenna, and this is the receiving antenna. We have calculated the phase difference due to the direct path and also the indirect path. So we have calculated the phase difference due to this path difference D2 minus D1, due to the difference of two paths D1 and D2. And here there is another wave here, which we call it as a ground reflected wave. So here there is some phase angle variation here. This is the transmitting antenna height and this is the receiving antenna height. There is another phase change of beta. There is a phase difference of 180 degrees due to reflections from the ground. So let us assume this as beta. This angle as beta. So alpha represents the phase angle due to the path difference and beta represents the 180 degrees, which is the ground reflected angle. Now the total phase difference theta is given by the two phase differences. So hence the total phase angle is given by theta is equal to alpha plus beta. Theta is equal to alpha plus beta. So alpha means due to the path difference, beta is the reflected wave, the ground reflected wave. So the summation of these two phase differences gives the total phase difference theta. Now let us calculate our objective is to find out the electric field strength. So what is the amount of electric field strength reached to the receiving point? Suppose there is a distance of d here. This is the height of the transmitting antenna and this is the height of the receiving antenna. So how much amount of electric field strength is going to reach to the receiver antenna? How much amount of electric field strength is reached to the receiving antenna for a given distance of propagation? It is given by ER is equal to E naught into 1 plus K e power minus j eta. This is the general expression to find out the field strength. The general expression to find out the resultant field strength at the receiving point R is given by ER is equal to E naught into 1 plus K e power minus j theta. K is a constant of proportionality here, and we know that the theta represents alpha plus beta. So theta represents alpha plus beta. So ER is equal to e power k into e power minus j theta. So according to the trigonometric series, we know that e power j theta is equal to cos theta minus j sin theta. So cos theta minus j sin theta. So this is e power minus j theta here. We are represented here. Let us find out the magnitude. Let us find out the magnitude. So to find out the magnitude, if we take the modulus, let us take the modulus of electric field strength. If we take the modulus of electric field strength at the receiving arena, you will get E naught into root of 1 plus K cos theta whole square plus K sin theta whole square. So we can write this as in the form A plus JB. We can write as 1 plus K cos theta minus K J sin theta here. And here we can write a 1 plus K cos theta as one expression minus J into K sin theta. J into K sin theta. We assume this as A and we assume this as B here. So if we take the modulus A plus JB here, for this A plus JB we can write as A square plus B square. So modulus of A plus JB is equal to a root of A square plus B square. So the same thing we have seen here, E naught into root of 1 plus K cos theta whole square plus K sin theta whole square. Here this is the K sin theta represents B. Here there is 1 plus K cos theta, this represents A. If Earth is assumed to be the perfect, let us assume Earth to be perfect. That is the conductivity, permittivity are perfect or 0. So then Earth is said to be perfect. So in that scenario, the K is assumed as 1. If K is assumed as 1, so let us simplify this. Once we can apply A plus B whole square. If you apply A plus B whole square, you get 1 square plus K square cos square theta plus K square sin square theta. And in this, we can take K square as common here. If we take K square as common here, you will get cos square theta plus sin square theta. So cos square theta plus sin square theta is equal to 1. And again, you will get here 2K cos theta also. So 1 plus K square plus K square cos square theta plus K square sin square theta will get here. You can see here, if we simplify this here, E naught into root of 1 plus K square cos square theta plus 2K cos theta plus K square sin square theta. So here K square cos square theta, K square sin square theta will get simplify. You will get K square into cos square theta plus sin square theta is equal to 1. So here, if you simplify the expression, you will get E naught into root of 1 plus K square plus 2K cos theta. 2K cos theta. And here, cos theta can be written as according to trigonometric theory. We are having formula cos theta is equal to 2 cos square theta by 2 minus 1. So cos theta is equal to 2 cos square theta by 2 minus 1. If you substitute this here, you will get 2 into cos square theta by 2 minus 1. If the perfect or the K is treated as 1, hence substitute K is equal to 1 here. So you will get 2 plus 4 cos square theta by 2 minus 2 here. So minus 2 plus 2 get cancelled here. You can see here, get cancelled here. And if you simplify this, you will get square root of 4 cos square theta by 2 means you will get 2 cos theta by 2. You will get 2 cos theta by 2, which is ER value. So, but we know that theta is equal to alpha plus beta. We know that theta is equal to alpha plus beta. Let us substitute this theta is equal to alpha plus beta in the above expression. We have substituted here theta is equal to alpha plus beta, where beta is equal to 180. So we have substituted here, you can see here pi, 180 means pi here. So we can write this expression as 2 E naught cos pi by 2 plus alpha by 2. So you will get cos 90 plus theta is equal to minus sin alpha by 2. So as we are taking the modulus, take this modulus, you will get sin alpha by 2. sine alpha by 2. So you can substitute this alpha value here. You can see here the alpha value is 4 pi h t h r by d lambda. So from equation 6 we have seen the value of alpha here. This is the alpha value 4 pi h t h r by d lambda, and you can substitute this alpha value 4 pi h t h r by d lambda in this expression. So we know that d is far greater than hd or hr, right? So the distance between the transmitting and the receiving end will be in terms of kilometers, and hd will be in meters, hr will be in meters, right? So the distance is very large and hd and hr. So according to this assumption, since d is far greater than hd or hr, we can write sin theta is equal to theta. We can write this sin theta, that means for larger value of distance. For larger value of distance between the two antennas, sin theta becomes theta. Sin theta will be equivalent to theta, approximately equal to theta. So here, if we apply this assumption, sin of 4 pi h t h r by 2d lambda will be equal to 4 pi h t h r by 2d lambda is equal to 2d lambda. So this we have simplified here, sin alpha by 2. As we are taking the modulus here, we will get sin alpha by 2. So this we are getting as ER is equal to 2 E naught into 4 pi h t h r by 2 lambda. So you can replace this with 4 pi h t h r by 2d lambda. So after replacing, you will get 2 E naught into 4 pi h t h r by 2d lambda. 4 pi h t h r by 2d lambda. So further simplification, 2 and 2 get cancelled here. So with the remaining things are E naught into 4 pi h t h r by d lambda. So here this ER represents the electric field strength at the receiving antenna. ER represents the electric field strength at the receiving antenna. And let us assume EF. EF as the field strength of the direct ray, the free space field strength at the unit distance is given by E naught is equal to EF by 2. EF by D. So ER represents the electric field strength at the receiving antenna. E naught represents the electric field strength in free space, and EF is the field strength of the direct path, and E naught represents the electric field strength at a unit distance from the transmitting antenna. So we are having the relation between the E naught and EF as E naught is equal to EF by D. E naught is equal to EF by D, and EF is equal to 7 root P. We know that EF, the field strength, EF is the field strength of the direct path. It is given by E naught into D, where EF is equal to 7 root P. So P represents the power. P represents the power transmitted by the transmitting antenna. So we substitute these equations in the above expression here. So E naught is equal to, so this equation can be modified as ER is equal to, E naught is equal to EF by D into 4 pi HT HR by D lambda, and EF is equal to 7 root P. 7 root P by D, 4 pi HT HR by D lambda. So if we simplify this, 7 4s are 28 here, and 28 3s you will get approximately 87.8 something here, 87.88. So overall you will get 87.88 HT/HR by D square lambda. So if you simplify and substitute E naught value and EF value in ER equation, so you will get 88 approximately 87.92 root P HT/HR by D square lambda, and this 87.92 can be rounded off to 88 and it is nearest to 88. So we can write as mod ER is equal to 88 root P HT/HR by lambda D square. So mod ER is equal to 88 root P HT/HR by lambda D square. So you can substitute here, you can simplify here, 7 into 4 is equal to 28, and 28 into pi, you will get 87.92 here, and this root P is as it is. P represents the power transmitted by the transmitting antenna, which is denoted in terms of watts here. HT is the height of the transmitting antenna, which is represented in meters, and HR is the height of the receiving antenna, represented in meters, and D is the distance between the transmitting antenna and receiving antenna, and lambda is the wavelength, that is the operating frequency, operating a signal frequency of the transmitting antenna. So these are the parameters which we have, which we are going to define in the amount of electric field strength received by the receiving antenna. So here from this expression we can observe that the electric field strength that has been produced by the receiving antenna, absorbed by the receiving antenna, it depends upon the power transmission P. It depends upon the height of the transmitting antenna. It depends upon the height of the receiving antenna, and it also depends between the distance between the transmitting antenna and the receiving antenna here, and also depends upon the frequency. So this is the derivation regarding the field strength of the space wave. So just now we have discussed the line of sight communication. So the line of sight is that distance, that is the distance between the transmitter and the receiver. You can see here in the figure, in which the direct ray passes from the transmitter to the receiver, so without being intercepted in the earth surface. So there is no any obstacles between the transmitting antenna and the receiving antenna. There is a direct path is established between the transmitting antenna and the receiving antenna, and we call it the path as line of sight path. So the wave travels with a minimum distance, and more amount of signal can be absorption takes place by the receiving antenna in the line of sight communication. So which means it travels to the distance up to which a naked eye can see. So we need, for establishing the line of sight communication, see that the receiving antenna is aimed towards the transmitting antenna, aimed towards the receiving antenna. So we need to employ an amplifier come transmitter here to amplify the signal and transmit again. So line of sight communication is one of the important concepts in the space wave propagation for operating very high frequencies ranges. So with this, we close the session here. Today we have discussed what is the space wave propagation, and we also discussed about the field strength derivation, derivation here of the space wave propagation. So which is given by ER is equal to 88 root P HT by D square lambda, and space wave propagation is applied only for very high frequency and ultra high frequency ranges. So about 30 megahertz range of frequencies can be propagated in the tropospheric region. The tropospheric region is around the range of 10 to 20 kilometers from the surface of the earth. So for reference, these are the reference textbooks we have, just whatever we have discussed now. If you want to go through the notes, you can see through the textbooks as seen in the slide. That is Anderson wave propagation by Bakshi, Anderson wave propagation by K.D. Prasad, and you can also refer Balanis also. You can also refer the author Balanis for the space wave propagation topic. Let us close the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.